As usual, let's do a couple of quick course business announcements. So exercise 6 is up. I apologize, I have not yet uploaded the marks for exercise 5. It's just a bunch of data entry that I haven't gotten to yet. So hopefully I'll get that done today. Notice that the exercises for this week are all symbolizations. We're going to take a break from derivations this week. I hope you don't forget them entirely. We'll come back to them next week, I promise. If you're missing them, I promise. You can go back and do ones from the last chapter if you want. If you missed derivations real bad, you can just do them for fun, you know, okay? So another thing to note here is the first 5 are all skills we'll do today. The second 5 are skills we'll do on Wednesday. So if you see the second 5 and you're like, I don't know how to do this, that will be why. You could probably work out from everything that I've said so far how to do the last 5, but we won't explicitly cover it until Wednesday. Okay? And another thing to note, so this is going to become more relevant the deeper we get into this stuff, and it's sort of like, it's quite relevant now. The fact is that Logic 2010 does not recognize all of the logically equivalent ways of symbolizing these sentences. This is something that Logic 2010 tells us explicitly. There's little disclaimers built into the FAQs and stuff. They say, look, we've got a bunch of the logically equivalent ways of symbolizing these built into the program, but there are some that we missed. We didn't get them all. So if you're, at this point, if you're putting something into Logic 2010 and it's telling you it's not right, it has become possible that it is right, that you would get a correct answer on the test or the exam. Nonetheless, Logic 2010 isn't recognizing it. So I just want to flag that for you as a possible thing that might happen. If that happens to you, if you're like, look, I just cannot figure out a way in which this is wrong, try a logically equivalent version of it. Try something that says the same thing, but in different symbolization. Get on Quarkus. We'll talk about it. We'll try to figure out what's going wrong. OK? Sorry about that. I mean, it's just sort of the limits of the program. It is a human being has to type in which are the logically equivalent versions. The actual computational procedure for working out all of the logically equivalent versions would be horrendously intractable. So that's why they didn't do that. So that's why that limitation exists. And I just want to flag this for you in case you run up against this limitation. So if you're in a situation where you're like, I swear this is right, this has got to be right, but it's telling you it's wrong, that might be what's happening. OK? OK. Any other course business? Any other course questions? Admin questions? Anything like that? All right, we're all settled in. Good. Let's do some content. So we're going to do symbolization and predicate logic. We started a little bit of it last time. We're going to spend this whole week just getting into this. So recall the fact that we've got 2 quantifiers that we're working with. The backwards E says there exists something such that X, and the upside down A says for all things X, blah, blah, blah. Okay? And recall also that we can understand what these quantifiers say by thinking about how these variables could be we could substitute names into where these variables are. So the existential quantifier says, you know, I've got a list of names. So I suppose I've got a list of all the names of everything in the universe. Name that chair George, and that one Fred, and that one Bill, and that one Hank. They've all got white guy names, but that's fine. So you've got a list of all the things, all of the objects in the universe, and you've given them all names. You're going to run out of letters. You're going to probably have to use numbers, but that's fine. Now, the existential quantifier says somewhere in that list, there's at least one name that I could plug in where this variable stands and get a true sentence out of that. There's at least one. Could be more than one. That's perfectly compatible with the existential quantifier. All the existential quantifier says is there's more than 0. There's at least one name that I could shove into where this variable is and have it spit out a true sentence. Yeah? The universal quantifier says for every single name on that list, every name in the universe, if I stick that name in here, a true sentence will come out. Yeah? So you can go along for every name in the thing. So one way of thinking about the universal quantifier is as a kind of elaborate conjunction. So if I say for all x, if x has property f, then it has property g, that's kind of like saying if A, so these are all names because they're the first half of the alphabet. If A has a property f, then A has a property g, and if B has a property f, then B has a property g, and. So the universal is kind of just like a humongously long conjunction, set of conjunctions, saying this name has this property. You know, the sentence is true about this name. The sentence is true about that name. The sentence is true about the next name for every name in your universe of discourse. Okay? So just to get refreshed on what these quantifiers say. I think we said something equivalent to this last time, but just to kind of get you primed again. Okay? Okay with that? Okay, so this is a way of thinking about what the role of, so the relationship between quantifiers, names, and variables is going to be really important to get clear on. And this is maybe one way of thinking about that relationship between those three things that we've introduced in predicate logic. This is again why it's also really important to use the right letters for variables and names, because variables and names act very differently in predicate logic. Right? They're very different objects. Okay. So now let's talk about scope and binding. Scope and binding. A variable that's attached to a quantifier, we say, is bound to that quantifier. Right? The quantifier ranges over that variable. So the variables that a quantifier is bound to are its scope. Okay, so what does that mean? That means the following. So a quantifier can only bind a variable if it's within the scope, and atomics right after a quantifier are within its scope, and things within the brackets right after a quantifier are potentially in its scope. Okay, so get to some examples here. Right, so the simplest examples, of course, one quantifier and one atomic for all x, fx. Recall how improbable a sentence this is. You're probably not going to make many sentences of this form, because what that sentence is saying is for everything in the universe, everything that you could name, it has the property f. There's not a lot of properties like that, right? Not even mass. Okay, but the scope of that quantifier x is just the whole sentence that precedes it. That's the simplest case. A slightly less simple case is when you've got some complex sentence after the quantifier. So within the brackets there, that for all x, x ranges over all of the x's that appear in the brackets after it. Okay? And what that means is, if you're applying that test that I just described, so this says, for everything in the universe, for all x, any name that you could put into x, this sentence will be true. And if you're under the scope of a quantifier, that means that every instance of x gets the same name replaced into it. So if you say, you know, if A has the property h, then A has the property g and b. Right? So it's not that you do this test one like name at a time, and the scope tells you which name you're substituting into each slot. So this does not say, for example, this does not say for all x, if there exists any x with the property h, then some other thing has the property g and b. It's got to be the same thing, the same named object going into each of the variables, right? All the x's get the same thing. So we're talking about one object. If it's got this property, then it's got those two properties. Okay? That's what it means to be under the bound to a quantifier. It's that if I'm placing something into x, it goes into all the instances of x within the scope of that quantifier. Okay? Okay. Now here's a sentence with two quantifiers, two separate scopes. There exists a y such that y has the property f, or it has the property g. The scope of this y is the whole sentence that comes after it, the whole sentence in the brackets after it. That's going to be the typical case. But this quantifier does not extend to the for all x statement. So that the scope of this is done. The thick line underneath it is indicating the scope of these quantifiers. So if there was a y over in this right-hand sentence, that y would not be under the scope of this first quantifier. Okay? This sentence is sort of done saying something about y. And then the scope of this quantifier is just the stuff after it. Okay? So far, all we're saying is either the scope of the quantifier is defined by either just an atomic that comes right after it, in which case it doesn't need brackets, or just whatever's inside the brackets right after the quantifier. So that's, I mean, it's kind of easy to determine what the scope of a quantifier is because it's just whatever's in the brackets. Yeah? Okay. Okay. Some slightly more complex cases, you can have quantifiers within quantifiers. The scope of the quantifier within a quantifier is still the brackets that come right after it. So that we got this thing that says for all x, if hx then lx. The scope of that quantifier is just the stuff that comes immediately after the brackets, or within the brackets that come immediately after the quantifier. Right? So in this case, x is bound to that for all x. The scope of the there exists y that's out front there is the whole sentence. Yeah? And the second example is just the same thing. The scope of so it says there exists an x such that all of this stuff, the scope of that quantifier is just until the brackets end. You know, you start a bracket immediately after the quantifier. Whenever that bracket ends, the scope is the whole thing there. Yeah? And then the scope of the embedded, there's a quantifier embedded in this sentence. The scope of that is just wherever its brackets end. Okay. So far, this should be, there's not really any tricks here so far. Are we okay so far with this? Okay. None of you look happy, but none of you are objecting, so I'm going to move on. All right. Okay. So here's a trickier case. You can use the same variable in two different sentences in the same string, and the scope is different. The scope is different. I don't know how you even opened that door. That's impressive. I don't know how that happened. I want to go ask him. Okay, sorry. Okay. So there exists a y such that fy and gy. The scope of that first quantifier is whatever comes after the brackets, just like we've discussed. Now, we've introduced another quantifier in the right-hand side of that conditional. We say for all y, if hy, then ly. Now, the trick here is that it doesn't have to be the same y. It doesn't have to be, we're not necessarily talking about the same thing here, right? So if I slot a name into this first half, the existential half, so for a, there exists some thing such that it's got both the property f and g, and suppose that's true, then this second thing follows, but it doesn't have to be the same name slotted into the second one. It's kind of an annoying way to write a sentence. Like if you were being nice about it, you just use a different variable, because why not? Right? So if you're doing symbolizations, probably you want to use different variables for your different quantifiers because it makes it clearer. This is hard to read somewhat, but it's perfectly logically okay. And the thing to note is whatever you slot into the first sentence doesn't have to be the same thing as you slot into the second sentence. Could be. It could end up being the same object. So if there exists some object that has properties f and y, then that object still falls under the scope of this universal quantifier, right? But it didn't have to be the same thing. That's the trick. And that's why, so the scope of a quantifier is really important, because once you're done with the scope of a quantifier, you move on to the next sentence, and it could be talking about entirely different objects, even if it's got the same variable. Yeah?
Just to clarify, so the y behind the f and g should be the same thing, right?
That's right. That's right. So within the scope of a quantifier, so the question is, the y within there exists a y such that fy and gy. Those fy and gy have to be the same name that you're plugging into it. You're not actually going to be plugging names into it. You're just imagining that you are. But so there has to be something that satisfies both y and g. It's got to be the same thing because they're both within the scope of the same quantifier. Whereas the hy and ly on the right-hand side of this are in the scope of a different quantifier, so they can be different objects. It doesn't have to be the same because it's under the scope of a different quantifier. Okay? Okay. I mean, when you're symbolizing, maybe don't do this because it makes things confusing for you and for us. But there's nothing wrong with, there's nothing logically wrong with this. Okay. Okay, so another scope and binding rule. So there are 3 scope and binding rules we're going to learn today. A variable is bound by a quantifier only if it's the same letter as the quantifier. So for all x, this thing, and if you have gy in there, that gy is not bound by the for all x. It's just the same. A quantifier only binds the same letter as comes after the quantifier. That should be fairly intuitive, right? Okay? Here's an odd one. You can have, if I was designing logic, I wouldn't have let them do this, but they did it anyway. So you can have nested quantifiers where there's a quantifier inside the other one that uses the same variable, and that's okay. But what this sentence says now is there exists some x such that x has the property f, and there exists some x such that these two things, but it doesn't have to be the same x. This is annoying, I know. But so once you've introduced, so this x has to plug into here, but once you've introduced a new quantifier nested within the larger quantifier, the scope of this quantifier is just the brackets after it, and this x is bound to the innermost x, not the outermost one. So the innermost quantifier takes precedence in binding. Yeah? And annoyingly, they don't have to be the same object here. So this sentence can come out as true if there's some object that has the property f, and there exists some totally other object that has the property that there exists a z such that g, and that other property has the property h. So this could be, this one is Roy, and then there exists an x such that, this is Tim. Tim satisfies this sentence. Roy satisfies this sentence. They're different objects, but they use the same variable. This is an especially annoying way of writing a sentence, an especially unclear one for us feeble human minds, but is nonetheless still logically fine. Okay? And the rule is whatever the innermost quantifier is takes precedence for binding. Yeah?
So every time you introduce a new quantifier, it will have its own scope.
That's right. Every quantifier has its own scope, and the scope is determined as basically either if there's an atomic right after it, the scope is just the atomic, or whatever's in the brackets. Yeah. Yeah. So every quantifier has a scope. Yeah. Yeah. And there's an example of the scope being very limited because there exists a z such that gz, there doesn't have to be brackets, it's just the atomic right after it. Okay. Yeah.
Why is the EZ, GZ bound
Yep.
to the EX if it's a different atomic?
So anything within the brackets is under the scope of the quantifier that the brackets are attached to. So there exists a z such that gz is within the scope of the quantifier, there exists an x. Because anything within those brackets is under its scope. Now they've got different letters, so the fact that there exists a z such that gz isn't really affected by there exists an x such that blah, 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 right? So because they're different letters, they don't really interact logically. but nonetheless, it's within the scope of that there exists an X. Yeah? Okay. Okay. So now we're going to distinguish between a free variable and a bound variable. So we've been talking about under what conditions is a variable bound to a quantifier. A free variable is a variable that is not bound to any quantifier. And you'll see free variables in your derivations. So it's not like they're ruled out entirely. It's not like they're logically incoherent. But you should never end up with free variables in your in your symbolizations. Sorry. When you're symbolizing things, you shouldn't ever end up with a free variable, because free variables don't really, like, it's really hard to say what they would mean in English or in natural language more generally. So here are some sentences with free variables. For all x, if fx, then gy. And there's no, y is a variable because it's in that part of the alphabet, but there's no quantifier that binds y. And I don't even know how to say that sentence in English. So it would say, for all things x, if that thing has the property f, then gy. Like, I don't even know how to articulate that as a sensible sentence in English, because you're missing the, there is something such that part of the sentence, right? Something G. It doesn't make sense as a sentence, which is why they should never, when you're trying to symbolize a sentence, which presumably does make sense, you never end up with a free variable. Yeah? If you end up in your symbolization with a variable not bound to a quantifier, something has gone wrong. Okay? Similarly down here, the left-hand side of this is perfectly fine. Both of our x's are bound to there exists an x. But we've got, on the right-hand side, a not jx that is not bound to the scope of any quantifier. And you might be tempted to say, I've seen x before. That was in the first half of this thing. That's what I'll bind it to. But that's wrong, because the scope of this quantifier ended with the brackets, right? It says these are two fully separate sentences. There exists an x such that if fx, then hx. Good. And then the scope of that quantifier is done. Now we started up a whole new scope of this quantifier for all y. And this x is hanging out not within the scope of a quantifier that ranges over x's. So this is a free variable, and I can't say that. There's no English sentence that makes sense that I could say there. Yeah? Yeah?
In the case of an embedded, you could still apply to x, though, right? Because x's scope goes across the whole.
Yeah. Okay. So let me try to make. I think what you're saying is the following. If we did that, that would be okay. So now, by moving the bracket to include the second generalization, what I've done is I've widened the scope of the quantifier, the first quantifier, to include the x that was just kind of dangling free there. Okay? Okay. So now that bottom one could make sense in a symbolization, because the final x is bound to the first quantifier. Yeah, I said this already. It's not that free variables are verboten in logic. They will turn up in your symbolizations from time to time. But that's okay, because you don't have to try to read out your symbolizations or make sense of what they're saying. In fact, it's probably better if you don't. Your humanity and understanding is slowing you down. But when you're symbolizing, you are trying to make sense of something. So if you symbolize and you end up with a free variable, that means that you didn't symbolize it properly, because the sentence you started from should make some kind of semantic sense. Even if they're bizarre and convoluted, they still are supposed to make sense. and so don't end up with free variables. All your variables should be bound by some quantifier or other. Okay? So that was free variables. Okay, good with that? That was scope and binding rules. So just to review, these are the three scope and binding rules we just looked at. These define the necessary and sufficient conditions for a variable to be bound to a quantifier. The variable is within the scope of the quantifier. Typically, it's within the brackets right after the quantifier. I mean, there will be some atomics, but like mostly brackets immediately after the quantifier within the scope. It's the same letter as the quantifier. You don't bind all of the variables in the sentence. You only bind the letters that are the same as your quantifier letter. And it's not already bound by another quantifier. That we have to include that because we had these weird cases where there's one quantifier embedded in another quantifier and they use the same letter, that kind of thing. So that was what that was. Okay? Scope and binding. If this doesn't feel intuitive yet, it's probably because you haven't started doing all that much with these sentences. So once you start manipulating these sentences, these rules will become skills rather than just sentences I'm saying at you. Yeah? Okay. And one last thing to note, names are not bound to anything. Right? You don't need to bind a name to a quantifier. A name names a specific object, A, an. So for all objects in the universe, if an has the property F, then that object has the property G. So we only need to bind a variable to a quantifier because the variable says something about all objects, right? If you're saying something about a specific object, you don't need to be bound to a quantifier. It's not these quantifiers give us general statements about the existence of something such that, or that all things have this property. Those are both general statements. A name is a specific statement, saying something specific about a specific object. So you don't need to be bound to a quantifier. Names are always just fine all by themselves. Okay? Okay. So that was the relationship between variables, quantifiers, names, and scope. 4 things that we have to sort of keep well related to each other. All right? Okay, so these are just kind of syntactic rules that we're going to use in our symbolization work and our derivation work eventually. Okay. I think that's it for this. Is there questions or concerns about that? Possibly questions and concerns will come to you later. So let's keep this open and come back to it. Okay. So now we're getting so that was a bit of sort of syntactic preparation work. We're getting used to the formalism, what the formalism means. Now we're ready to go sort of deep or directly into the symbolization work. Let's do some how do we symbolize sentences stuff. Okay. So here are 4 categories of categorical sentences. I should have picked a different word. Here's 4 kinds of categorical sentences. You'll see, you'll note that categorical doesn't just mean universal. It's just these general sentences, the sentences that you use quantifiers to symbolize. And this is like Aristotle level logic. This is something, if you showed Aristotle this lecture, he'd be like, yeah, I wrote all that out. That's fine. So let's distinguish the universal affirmative. Every A is B. You are affirming something about everything. Universal affirmative. From the particular affirmative, some A is B. From the universal negative, no A is B. From the particular negative, some A is not B. We'll go through these each one by one and talk about how they get symbolized. So, the universal affirmative. The most typical way of symbolizing this is if, so for all x, if fx, then gx, or whatever variable or letter you're using. For all x, if x has the property f, then it has the property g. So we saw this last time, right? This is the one that we did a little bit of last time. Is it clear why this is the universal affirmative? Is it clear why you don't want to say for all x, fx, and gx? Because that's the one you might be tempted by, and that's a radically different sentence. What am I saying? If I said for all x, for all x, fx, and gx, what am I saying?
There goes F and G.
Yeah.
Axis,
Yeah. So every object in the universe has properties f and g. And that's not what we're trying to say with, we're not trying to say, we're trying to say all dogs are happy. We're not trying to say everything in the universe is both a dog and happy. Every electron, every moon, and every distant planet is both a dog and happy. What we're trying to do to make the universal affirmative, what you have to do is restrict the scope of what you're talking about. You have to carve out some subset of the things of all of the names of everything in the universe. You have to say, look, I'm just talking about these things, right? I'm talking about all the flies, or whatever it is. So of all the x's such that x is a fly, those things have this property g, being giddy or something. Yeah? So the antecedent restricts your domain of discourse. You're saying, of these things, and I'm only talking about these things, they have this property. This is where it's useful for, I mean, our conditional is really weird because it's always true when the antecedent is false. But that's helpful here. That's why this is helpful here, because if you say, look, of all of the flies, they are giddy, you don't want that being falsified by there being something that's not a fly, right? You don't want that to be the case. You want that sentence to come out as true. When you stick a name for something that doesn't satisfy the antecedent, you want it to come out as kind of automatically or vacuously true, right? It's really only in the cases where the antecedent is satisfied that these conditionals get tested, right? Suppose there's a non-giddy fly, a fly that's not giddy, then we have something that satisfies the antecedent but not the consequent, and so the thing comes out as false. Right? So the antecedent tells us what the topic is. And then the consequent is some assertion about that topic. We're saying all of those things within my restricted domain of discussion, all of those things have this property. So that's why we do that with this conditional. Okay? And you can get elaborate with that, right? So you can get more complex antecedents. The more you pack into the antecedent of one of these universal affirmative claims, the more specific you're getting. So for all things x, if x has the properties e and f, then they have the property h. So let's suppose that's saying all things that are both elephants and friendly are herbivores. So we've restricted our domain of discourse twice there. We're saying we're only talking about the elephants, and we're only talking about the friendly things, so the things that are both friendly and elephants. Now I'm going to make a claim about that doubly restricted domain, that they're herbivores. Now, people don't talk like the first two sentences here, right? That is not how anybody would phrase anything, unless although I find myself talking more, and the more logic I do, the more I start talking like this. It's kind of it's worrying, actually. A regular person who is not neck deep in logic would say the following: all friendly elephants are herbivores. That's a regular sounding sentence, right? That's the kind of thing that people say, if I recall correctly. So you have to pick apart this sentence, all friendly elephants are herbivores, and figure out which parts of it are being used as restricting the domain of discourse and which parts of it are being asserted about that domain. Right? So basically you look at a sentence like this, all friendly elephants are herbivores, and you want to try to separate out what goes in the antecedent and what goes in the consequent. If I'd said instead all elephants are friendly herbivores, now I've shifted friendly from the antecedent to the consequent, right? That would be saying instead, so if I say all friendly elephants are herbivores, or if I said instead all elephants are friendly herbivores, how would that affect this sentence here? It would shift friendliness from the antecedent to the consequent. Yeah? So this says all of the things that fall under the category of elephants have the following two properties, both being friendly and being herbivores. Yeah? So the skill here is being able to figure out what's being used, which parts of the sentence are being used to carve out the topic, and which parts of the sentence are being used to assert something about that topic. Good? Okay, we'll see many more examples of this as we go along. Okay. Here's another way of doing the same basic thing. You could equally have said that using a series of conditionals, right? So we could say for all x, if something is an elephant, then if it's friendly, then it's an herbivore. And those conditionals do the same work as putting it as an and statement, conjunction, in the antecedent. So those two ways of putting this are logically equivalent. Those are just as good as each other. They are both perfectly valid ways of symbolizing this sentence. Both are doing the work of narrowing down. So the EX then FX or the EX and FX are both doing the work of shrinking down the topic that we're saying something about. We're not just talking about all elephants, we're talking about all friendly elephants. The natural way of saying those out loud is slightly different, but I hope you can see that they're both just doing the same job, which is narrowing down the topic and then making a single assertion about it. Okay? Logic 2010 is reasonably good at accepting both of these, in my experience. Yeah. Okay. Questions? Good. Okay, and I said this already. Here's how not to do this. Don't say for all x, ex, and fx. That is saying that everything in the universe is friendly and everything in the universe is an elephant, which is a very different statement than saying all elephants are friendly. That's it's unrestricted in its scope of discourse, right? So universal claims, unless they're a very odd universal claim, like all things are real or something bizarre like that, they're much more likely to be a conditional than a conjunction like this. Yeah? There are a couple of examples in the textbook where it's neither of those. So the example from the textbook is all things are either mental or physical. So that's a disjunction, plausibly true sentence. Everything's either mind or matter. But that's a very rare, like you basically have to be doing metaphysics to get anything but a conditional to work in this sense, right? So if you're trying to symbolize a universal affirmative, really good bet that you're going to want to use a conditional statement. And you're going to want to use a conditional statement where you're first narrowing down the topic of discussion by putting as much as necessary into the antecedent and then making some claim about it. Okay? Okay. The particular affirmative. There exists something which has both the properties J and K. This is fine as a conjunction Because we're not saying that everything has the properties J and K. We're just saying there's at least one thing. Equivalent natural language versions of this, some J's are F's, or some J is F. The second one there, some J's are F, sounds kind of like a universal claim because it's plural. You might be thinking, oh, we're saying of all the J's that maybe they're F's. But that's not what that sentence says, right? It's just saying some J's are F. And it implies that there's more than one. But since we don't have a quantifier between there's more than 0 and literally everything in the universe, we're going to symbolize some J's are F's as there exists at least one J that is F. Okay? So if you see some J's are F's, that's going to be an existential. Is that all right? Like, this is one of those points where maybe the logic doesn't exactly fit how you would intuitively think about it. But since there's no better way of doing that than the existential quantifier, that's how we're going to proceed. OK. Yeah?
Sorry, what did you say I meant K, right?
Boy, did I. Sure did. Yeah. Some J's are K's and some J is F. Yeah, those should be K's. Thank you. Good. There's my mistake for the day. Good. No. Yep, there it is. Yeah. Okay. Good. Does that count as 3 mistakes or just 1? It doesn't. Okay. Good. Okay. Good. Okay. Okay. A couple more. So, and again, here's how not to symbolize the particular affirmative. Don't do it the same way you did the universal affirmative. Don't do that. So this sentence says there exists some X such that if it is C, then it is a B. But this sentence is really easy to make true. It's really easy to make that sentence true because the conditional is true anytime the antecedent is false. So there exists a cat that can bake cookies. There exists an X such that X has the property C, being a cat. If it got the property C, then it's got the property of being a baker of cookies. Well, that sentence is not made true by the existence of things that are not cats, right? We all agree there are things that are not cats, and yet there are no cats that can bake cookies, right? So that sentence should not be true. There exists a cat that can bake cookies on the basis of the existence of non-cat objects. But if you do this as a conditional, that's what you get. There exists an X such that if I plug in a name there, the sentence comes out as true. Well, I'm Corey, and I'm not a cat. Therefore, the conditional, if Corey is a cat, then Corey can bake cookies, is true. Right? And that's bad. That's not logically equivalent to the sentence we were aiming for, which is there exists at least one thing that is both a cat and can bake cookies. So don't do that, right? To symbolize a universal affirmative or a particular affirmative, don't use the conditional. Okay. Universal negative. If anything is an A, then it is not a B. And here are 2 exactly as good as each other ways of symbolizing this. Here's 2 logically equivalent ways of writing that out. And one or the other might feel more natural and intuitive to you, and if that's the case, do it that way. These are just as good as each other. There's no logical reason to prefer one or the other. So I hope it's clear why the first one is a good symbolization of this. For all things in the universe, if that thing is an A, then that thing is not a B. The second one, there does not exist something such that is both an A and a B. I'm saying there's nothing in the universe that satisfies the following description. You can go through every name of every object in the whole universe, and if we check every single one, none of them are going to satisfy this. I mean, that's the way it's phrased in the second one. The first one is the more positive uplifting one that say, look, for everything in the universe, if it's got this property, then it fails to have this property. So the universal negative. Good there? Okay. And then the particular negative. There exists something such that it's not B, which is exactly equivalent to there is not the case that for all things, that thing has the property B. Okay. So these are everything that I've been showing you so far is kind of systematically related with each other, such that you can translate between a bunch of these kinds of categorical statements. So we're going to learn a rule called Quantifier Negation. You're going to use this in your derivations a lot. If you've got, it's not the case that for all x gx, then you can get there exists an x such that it's not gx. And if you've got, it's not the case that there exists a gx, you can get for all x not gx. These third and fourth lines are a little more complicated, but I hope you can see how they might be equivalent to each other. So the first two here are just doing the same moves up here, right? So it's not the case that for all x blank, then that's equivalent to there exists an x such that not blank. This is kind of weird to say in English, however. This middle term is kind of weird to say in English. You might prefer there exists an x such that fx and not gx. And I hope that you can see, or you will be able to see when I point it out to you, that not fx then gx is equivalent to fx and not gx by negation of conditional. Recall that derived rule we used in sentential logic. If you've got the negation of a conditional, you can get something like that. Yeah? So that's what makes those logically equivalent. We're getting from like very syntactic to more practical. So now we're getting into the very practical end of symbolizing things. So, you know, what to do if you see words like only. All right. So only works pretty much the same in predicate logic as it did in sentential logic. Recall what happens with only in predicate logic. Say, if x then y, symbolized as x arrow y. Only if x then y, symbolized as y arrow x. Yeah? So if whatever comes right after if, you recall, is the antecedent. Whatever comes after only if is the consequent. Same thing in this system. So only small dogs are yappy says for, and it's a, okay, so notice what we're saying here is a general statement, right? So we're saying of all of the things that are dogs that are small, wait, oh, that is not right. So, no, that's right, that's right. So of all the things, only small dogs are yappy says if it's a yappy thing, then it's a small dog. It's a false sentence, right? There must be yappy things that aren't small dogs, right? There must be. I don't know. Anybody got a yappy cat? You don't really yap. Anyway. But if I said all small dogs are yappy, rather than only small dogs are yappy, that says of all of the things that are dogs and they're small, then they're yappy. Do you see how those are different claims? The first one is a claim about all the things in the universe that are yappy. That's the topic of that sentence. So the topic goes in the antecedent. We say we're restricting our domain of discourse to all and only the yappy things. We're going to make a claim about them. And that's false if there's anything that is yappy but isn't a small dog. That would make that sentence false. If you had a yappy cat or a yappy capybara or something, that would make the claim that only small dogs are yappy false. Whereas the second one is saying something about all of the small dogs, that they're all yappy. What would make that false is if you had a small dog that was calm and not yappy, right? A non-yappy small dog would make that one false, that second one false. Okay? So this is just the same, logically the same as back in sentential logic, but now we're dealing with the mild complexity of having it not just what's in the antecedent and the consequent, but the antecedent being the topic and the consequent being the thing being asserted about that topic. Is that cool? Pretty good? Good. Okay. Okay. This is something that people have been asking about. We should have done this already, but let's do it now. Relative clauses. Relative clauses. So compare the following two sentences. Dogs which are frisky are cute. And dogs which are frisky are cute. Okay. Those are, I'm going to say, making potentially different claims. The first one is just ambiguous, I would say. The first one is just unclear what it's saying. And in normal human life, you would disambiguate this by making your voice go up and down, or by the context that you're in, like what kind of conversation are you having and with whom. That's what would sort out what you're actually saying with that first sentence. The second sentence, we've made it clear with commas, right? What you do if you were speaking to somebody, you would express those commas with little pauses in your sentence. The subtleties and complexities of human language, which we remember fondly but can no longer touch. So let's distinguish two kinds of relative clauses. Non-restrictive and restrictive. So a non-restrictive relative clause says two things. Two separate claims are being made in this case. This is the one where the commas. So the one with the commas, I'm going to say, let's take this as a convention here. If it's got these commas which sort of carve out a separate claim, then it's doing a non-restrictive relative clause, which is to say it's making two separate claims. Dogs are frisky, dogs are cute. Okay? And because we're doing predicate logic, those would be two universal claims. All things in the universe such that those things are dogs have the property of being frisky, and all things in the universe such that those things are dogs have the property of being cute. Okay? So that's a non-restrictive relative clause. Compare that to the other kind, restrictive relative clause. Dogs which are frisky are cute is actually narrowing its topic down twice. It's restrictive because you're restricting the scope of your discussion. You're restricting the topic of conversation two times to just those things that are both dogs and frisky. We're no longer making a claim about all dogs. We're making a claim about just those dogs that are frisky, that they are cute. Okay? So what I want you to be sensitive to is the distinction here between making two separate claims about your topic and making a restricted claim, a twice restricted claim about your topic. And the cue is going to be the commas. That's your cue. If there's commas in there, carving out a clause, this is the relative clause. Between the two commas here is the relative clause. If it's carved out with commas, then it's the non-restricted relative clause. That means it's making two claims. You're kind of doing an aside. Dogs, which by the way are pretty frisky, are cute. Right? You're doing like a little aside in your sentence, right? And that little aside is another independent separate claim that could be true or false, independently of the first one, because maybe dogs aren't all frisky. There are lethargic, lazy dogs, right? So that part of the claim is false, but they're all cute, so that part's true. Yeah? So the non-restrictive relative clause makes two claims, one of which is a kind of by the way, and the restricted relative clause is just narrowing down the claim that you're making. So the first one is the restricted relative clause. Those dogs which are both, those objects that are both dogs and frisky, so we packed two things into the antecedent. We've doubly narrowed down our topic and then made an assertion, a single assertion about that topic. And recall, we could have done this with two conditionals as well. So if we'd said, for all x, if dx, then if fx, then cx. Yeah?
Because it's an aside,
Yeah.
like in the overall sentence, like if you were to object to the sentence, wouldn't it be that you're objecting, like it would seem as though you're objecting to it, dogs being cute. Like you'd be like, yes, dogs are cute, but I don't think they're frisky.
Yeah. Yeah.
But the overall sentence, dogs are cute, like dogs which are frisky are cute. Well, that might be true. They're not frisky.
Yeah. Yeah.
I think what I'm just saying is that like so in the
I think you're getting the relevant distinction. Yeah.
Because I'm
Yeah.
getting confused because for me that would be okay. So even though your antecedent is false, the overall sentence still is true.
So okay. So
Which seems more like the first one than the second one. Whereas in the second one, if one of those two things is false, then it's not this and this.
right. Right. So in the second case, you could. I mean, if both of those aren't true, then the whole sentence is false, right? So if you're making two claims and you made one of them as a kind of bracketed off aside, and you're going to say like, look, not all dogs are frisky, you're still objecting to the sentence as a whole. But in the second case, what you're objecting to is just one half of it. You can say, look, sure, dogs are cute, fine, we can all agree on that. It's a weird fight to be having with somebody. But I'm going to object to this half of the sentence. I'm going to say, look, they're not all frisky. I had a dog who was very lazy and lethargic. So this half is false, but this half is true, right? So you're objecting to the aside, but not the other half of the sentence. Whereas in the restrictive version of this, where we're saying, I'm just talking about the frisky dogs, then the only thing that makes that false is a frisky dog that's not cute, which is obviously impossible, so it has to be true. Yeah? So, yeah.
How do you know that for the second sentence, symbolization that the main connected is a conjunction?
Well, with the restrictive clauses, it's going to be a conjunction because you're saying two things, basically. So if you see this, basically what I'm doing right now is sort of manually giving you the answer to the how do you know that it's the conjunction? Because I told you if you see a restrictive clause, then it's a conjunction, basically. That's why we're going through these specific types of sentences kind of one by one. So, yeah. Because it wouldn't, so I mean, you can consider the alternatives, of course. If I'm saying, if we made this a disjunction, we'd be saying either dogs are cute or dogs are frisky. And that's not really what's being said here, right? You're not saying, because that sentence would be true if dogs are cute but not frisky or frisky but not cute, but that's not what's being asserted here. You're asserting two things. And anytime you have a bunch of independent assertions, you're going to connect them up with and, basically. If you say, like, I'm asserting that this is true, and I'm asserting that this is true, and I'm asserting that this is true. Yeah. And that's just what you've done in a sentence like this is just make two assertions. One is just sort of embedded in the other. Yeah.
Yes. So I think there was one of the assignments that's very similar to this one.
Yes.
And what I did is that I used for all access, and if it's dx, then brackets fx and cx. So it would be like if it's a dog, then it would be frisky and cute. I know because you told us so it would be a conjunction.
Yeah.
Is there any specific reason why, or like it might be wrong for what I did?
Did Logic 2010 say it was okay?
It said not okay.
Oh, okay, okay.
It's like a lot of incorrect signs.
Okay, okay. Can you repeat for me?
Yes. So I did for all x
Uh-huh.
dx
Yeah.
and then bracket. Oh no, dx condition bracket
Yeah.
fx and
fx and cx.
And that's it.
Okay.
So notice
Yeah. Okay.
technically it's still a conjunction.
It is still a conjunction. It is still a conjunction. So what the sentence says is, of all of the dogs, they are both frisky and cute. So you've restricted your domain of discourse to dogs, but you're saying something about all of the dogs, and you're saying that they have both of these properties. So the thing that makes that not the right way of saying the sentence is the which. Which indicates that we're either making a second claim or we're restricting our claim. So it's a restrictive. The which tells you that you've got a restrictive clause. It's telling you that you don't. Basically, it's telling you don't have this. You don't have two things that are being asserted. So you could make a sentence that says this. You say dogs are frisky and cute. So now that's what that would say. Dogs, I guess that comma's extra now. Dogs are frisky and cute. That's how you would symbolize that. The which is what tells you that's not the right way of saying this.
Can you repeat which tells you either it's you need to restrict your
So which tells you that you're looking at a restrictive clause, relative clause, sorry. But it doesn't tell you whether you're looking at a restricted relative clause or a non-restrictive relative clause. The commas distinguish those two. So if you see which, you're like, okay, we're either making a separate claim, in which case you do the conjunction of the two claims, or we're doing the other thing, which is to restrict the topic twice. Yeah. I wish there was less clumsy language for talking about this. I don't like the phrase non-restricted relative clause, but here we are, so. Okay. Here's another thing that you're extremely likely to run into. Implicit universals. A good man is hard to find. Now, A is it doesn't sound like a universal claim, does it? You're saying A, you're like, well, there's at least one good man that's hard to find. But that's not what this sentence is saying, right? Right? It's saying, of all of the things in the whole universe, finding a thing that's both good and a man is hard. Right? It's an implicit universal. It's a universal that's not, you're not always going to get the all or every. What you have to be sensitive to is claims that are only made true by a whole category of things having that property. So these are categorical sentences that we're dealing with. If it's the case that the whole category of good men have the property of being hard to find, then your sentence is true. Okay? Another one. If dogs are well fed, then they are happy. There's no all or every. But that's not made true by there being one or two dogs that are both well fed and happy, right? It's saying something about the class of dogs, the category of things that are dogs. Okay? Okay. And just to remind you, so we did this already, but one more time. The two ways of narrowing the scope of the discussion that are exactly as good as each other, they are exactly equivalent in terms of symbolizations, using conjunctions to pack more into the antecedent, or using a series of conditionals. Just to remind you. Okay? Okay. Shall we do some examples? Okay. So, let's see if I remember how to do these. Shall we? Okay. No dog is happy unless every dog is fed. Okay, so just like with good old-fashioned sentential logic, the first thing to do is always to try to carve up the sentence to its largest parts, try to figure out what the main connective is. So, no dog is happy unless every dog is fed. Going to be the unless as the main conditional, right? And unless is always or, right? So we've got something or something else. And now we just look at the parts and try to symbolize those. So, no dog is happy. There does not exist a dog that is happy. So that is a perfectly good way of doing this. So, and how would I symbolize that? That was a very good rephrasing, but.
So they're like not existential.
Yeah.
And then dog, like dx, bracket dx, conditional hx.
No, that's not right.
Oh wait, it's conditional, so and x.
That's right.
And hx.
So if we said that there does not exist an x such that if it's a dx, then it's an hx, that's troublesome. So if you just ignore this negation here, that would say there exists something such that if it's a dog, then it's happy. And that's, again, that's made true because, sorry, you made an instructive mistake, so I'm going to harp on it. It's true just in case anything is not a dog, right? If there exists anything that's not hasn't got the property D, then that sentence comes out as true. So this sentence being false is a very demanding condition. What we want to say is it does not exist something such that it's a dog and it's happy. Good. Good. Equivalently, we could have said the following. For all x, if it's a dog, then it's not happy. Oh, it's so sad. Right? Okay, good. So there's that half. Unless every dog is fed. So every dog is fed. Probably going to be, I've said this already, but recall that for any of these general statements, you can do it using either the existential or the universal. Whichever one feels better in your head is fine. Yeah?
Universal x,
Yeah?
bracket dx,
Yeah.
fx.
Very good. These brackets are superfluous, but okay, so writing that out sort of nicer. Does not exist an x such that dx and hx, or for all x, if dx, then fx. Good. We could also have done every dog is fed as there does not exist a dog such that there does not exist an object such that it's a dog and it's not fed. Right? There are no unfed dogs. A far happier sentence than no dog is happy, I would say. Okay? So this thing or this thing would have been perfectly fine for the first half. This thing or this thing would have been perfectly fine for the second half. Those are all logically equivalent. Yeah?
We can't use a conjunction in the second half, the first one, first of the second half.
That's right. You cannot say for all x if dx and fx. or sorry, dx and fx. Because that would say all objects in the universe are both dogs and fed. Venus is a dog and it's fed. Mercury is a dog and it's fed. My left shoe is a dog and it's fed. That's why we need the conditional to restrict down the scope of our claim. And that's, I mean, and I hope that's clear why the existential, the negative existential here is saying the same thing. There's no object such that it satisfies both of these properties. And that also restricts it down. So there's no problem with Venus being both a dog and not fed because it's not a dog. Good? Good. Another. I'm just going to keep doing these until we run out of time, basically. Okay. Okay. Each dog is, this is kind of almost the exact same as the last one. Do you want to skip on to one that's more different? Or, yeah, okay. I'll leave this to the reader. Not that you're reading, but. Here we go, here we go. Do a big gross one. All right. I wrote down some of the answers, but I forgot to write down the answer to this one, so we're flying blind here. This could be a disaster. Let's see if we can all get through this. Okay, if every dog is well fed, and every dog is an animal, and every animal is happy, then every dog is both well fed and happy. Ugh. Gross. All right, all right. So, we've got a big funky conditional here. I think that's what we're looking at here, right? Say, if all this stuff, then all this stuff. Does that seem right to you? So we've got if every dog is well fed and every dog is an animal and every dog is happy, then this stuff. Does that seem right to all you? So we've got a conditional with the following structure, something, something, then something else. Okay. Now we take it one chunk at a time. Just be kind to your working memory and take it one chunk at a time. If every dog is well fed and every dog is an animal and every dog is happy. So forget about the if. We're just talking about this thing, which is pretty obviously a set of conjunctions, right? It's three things conjoined together. So something and something and something. That's going to be our antecedent. Now again, we'll just restrict this down. Okay, every dog is well fed. Okay, now we're at the point where I can wrap my brain around it. We've chunked it down sufficiently that I can like hold this all in my head all at once, right? Every dog is well fed. I think we did this one already, so I'm just going to write it down. For all x, if it's a dog, dx, then it is fed. And we'll take well fed to be equivalent to fed, if that's okay. I think that works. Yeah? Okay. Yep.
Does that form have three conditionals? Shouldn't it be two conditionals with one divided into two parts?
It is informal notation. Sorry, three conditionals.
Sorry, not conditionals,
Conjunctions. It's informal notation, but it is still a well-formed formula because putting the brackets either around the first two or the second two are logically equivalent. They all have to be true for the whole sentence to be true, so it kind of doesn't matter where the brackets go. If I'm writing anything out for myself, I put the brackets in because it helps me visually put it together into its parts. But this is, logically speaking, this is okay. It's informal, but it's okay. We're not fancy here. Okay. All right, so there's that chunk. Now we got every dog is an animal. Every, that's a universal, right? So, and for all x. We could do another, so let's, for all y, if it's dy, then it's ay. No problem there. We could have used x again because the scope of this quantifier ended here. But nonetheless, we'll use another one for clarity. Is that good? That chunk is good? OK, now every animal is happy. This bit, again, every is going to be universal. For all z, if it's an animal, our topic is animals, so we put that in the antecedent. And we're saying about that topic that they are happy. H, Z. OK. OK. Getting there. So that's our antecedent, right? If this whole big thing, then every dog is both well-fed and happy. So I'll just say, put one big bracket around all that. Therefore, something. Every dog is both well-fed and happy. Every, it's going to be a universal, right? OK, what's the topic of every dog is both well-fed and happy? Dogs, right? Every dog. So dx is the antecedent. And what are we claiming about that topic? Well, two things, of course. They are fx and hx. Oh. hx. Ta-da! We did it. Thanks for your help, everyone. Yeah.
So for the consequence of
Yeah.
that sentence,
Oh, I'm missing a bracket. Sorry. Go.
for all things x, dx, then fx, then hx.
That would be wrong. That would be wrong. So the question is, can you do a conditional here? And that's not exactly what's being claimed here, because that sentence would say, for all things, if it's a dog, then if it's well-fed, then it's happy. So that would be to restrict your domain of discourse. That would put something that should be in the consequent into the antecedent, basically. It's to put something into your restrictions that should be in the claim about the topic. What we want to say here is that everything in the dog category has both of these properties, that they're well-fed and they're happy. Yeah.
This is kind of going back to her point.
Yeah.
But in the antecedent of this one,
Yeah.
in which way would it come out as a different, would the truth value come out differently if you had for all x, if dx, then fx, and, I mean, I guess it's ay here, but ax. So for
Yeah.
everything that was a dog, it is well-fed and it is an animal.
Good. Good.
Why?
That's OK. Actually, so I think the question is, why can't we do the following? Tell me if this is what you're thinking.
Yeah.
Dx, then fx, and ax.
And this other thing with the
And this thing. Yeah, yeah. Can you do that? Yes, you can do that. That would be logically equivalent to for all x, dfx, dx, then fx, and for all y, dy and ay. Yeah. Because you're just, all you're doing is, because you've restricted because the topic is exactly the same in both of these sentences, and you're just saying it's got the property x and it's got the property a, you can pack both of those into the consequent. Yeah, yeah.
So yeah, just going. I was thinking about it because she brought that up earlier with the which statement,
Right, yeah.
where it is technically the exact same truth values. So the which statement had the dogs, which are well-fed, are animals,
No, I think in that case there were different truth values.
because it would be dogs are well-fed and dogs are animals.
Oh, I see, I see.
it
So,
would still be dogs are well-fed and animals.
yeah, yeah, you could do that. You could do that. But she was asking us, I think her question was slightly different.
Oh.
We'll have to review the video once this is all done to see if it was. But
Said it was because of which
yeah,
makes the difference.
yeah, that's right. That's right.
I think what I was kind of wondering is why. Because the which, even though it is an aside, it's still, like, logically speaking, the exact same claim.
Oh, so All right, let's.
Logic 2010 said it was wrong.
And Logic 2010 is our god. Okay. So, these are two different claims.
It was the
And they're two, so these are different claims because of the
no,
position.
those ones are different claims, but there was one that you deleted.
All right.
The
Well,
non-restricted.
It's under an implicit universal.
What?
Yeah.
No, relative clause is non-restrictive.
okay.
So the non-restrictive is saying two things.
Okay.
It's saying both for
Since it's deleted and we can't go back to it, let's move on. And if this remains a question once we've all watched the YouTube video, then we can address it next time, okay? Okay. All right, let's do another example. I would like to get a few more of these under our belts before we're done. Okay. So these are from in amongst the symbolization. These are symbolization questions not on the weekly exercise, but are like in that same section as the weekly exercise. So this is on the level you'll be asked to deal with. None but the brave deserve the fair. You're going to get sentences that aren't easily recognizable as any of the things. Like this is not a there for all things blah, 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 right? This is a weird one, and you're going to have to think about exactly what's being said in order to translate this into logic. So, none but the brave deserve the fair. Yeah?
this is the equivalent to an only. So if they deserve the fair, then they are the brave.
So, right, only the brave deserve the fair. Yeah, yeah, I think that's a reasonable way of parsing this. So we might say only the brave deserve the fair. None but is pretty much only. So only the brave deserve the fair. What comes after the only? The consequent. So the brave is our consequent, and therefore deserve the fair is our antecedent. So we want to say it's a conditional. Is it an existential or is it a universal generalization? It's a universal generalization. We're not just saying there exists some people who deserve the fair and are brave. We're saying of anything such that it's fair, they deserve the, for anything that deserves the fair, oh, no, not AX. Then they are GX. Okay, so none but the brave deserve the fair. If anybody's not brave, then they don't deserve the fair. If anybody deserves the fair, then they're brave. Those are all saying the same things, right? Do I have it mixed up? I was seeing worried hands go up, and that usually means I screwed something up. Okay, so the antecedent is deserves the fair. Sorry, just GX. Then fx. Okay, is that right now? Okay, good. Okay. Sorry. I like it when the sentences start with the same letter as the variable, because then I don't have to remember which is which, but. Okay. Can anybody think of a logically equivalent way of symbolizing this that's not this one? I mean, this is logically equivalent to itself, but that would be just to be silly. Yeah.
It is not.
Just say the sentence, and we'll
Okay,
yeah.
There does not exist something that deserves the fair and is not brave.
Good, good. So, it's not the case that there exists an object such that it deserves the fair and it's not brave. Yeah? Yeah.
So I'm noticing that like the universal and the existential sort of follow like the NC rule.
That's right. That's exactly right.
Where it's like GX then FX, and then the NC rule will change that to GX and not FX.
Yeah, exactly, exactly. That's how, yeah, exactly. And you can, so given a universal statement, you can get, Okay, yeah. Let's leave that as well. Let's leave well enough alone. Yeah.
But then to follow the answer rule, shouldn't the first one, the conditional be negated?
Yeah. So there's it gets complicated to follow the NC rule exactly because we'd have to like double negate it. It's we're going to prove these formally soon, and it involves the negation of the conditional or quantifier negation. So can we put a pin in that question and say we'll come back to it? Is that okay? So I'll show you why. I'll show you formally why these are equivalent next week when we start doing derivations with this stuff. Okay? Okay. Let's do another. Kettles boil quickly only if not watched. Okay. We're not just saying something about your kettle or my kettle. We're saying something about all kettles, so it's going to be a universal. So for all x, something, something. And that something, something is, what's the topic of this sentence? What is being claimed? What is the thing that something is being claimed about? Kettles. Kettles. So kettles, if something is a kettle, then okay, kettles, something, something. Boil quickly only if not watched. Okay, only if tells us that the thing after it is the consequent, meaning boil quickly is the antecedent. So we've got boil quickly, gx, then hx. Oh, sorry, if not hx. Close brackets. This is not watched. So if something is a kettle, then if it's boiling quickly, then it wasn't watched. That okay? Not all of you are happy with this, but none of you are objecting. Yeah?
Only if not watched, so shouldn't it be antecedent?
No, because what comes after the only if is the consequent. Right? Yeah. This confused the heck out of me because you want it for it to be only if flips the order of things around, but if the only if comes in the middle of the sentence, then you don't do the flip, or you do like a double flip. It's very annoying. But nonetheless, the rule is whatever comes after only if is the consequent. The thing that came before the only if here was the antecedent, so we just keep it in the order that we symbolize it. Yeah. This caused me genuine distress to get this to work out. Okay. Yeah.
How come it's not fx and then gx and then conditional?
Sorry, say again, fx and gx?
Conditional gx and then another conditional not hx.
That's what we did.
Oh, but why is it fx conditional gx the antecedent?
Oh, I see. So the reason why that's not equivalent, or why that's not a good way of doing this, is that this antecedent is satisfied anytime something is not an f. See, so it's not that we've restricted down our. What this does is, this is satisfied anytime. Well, yeah, anytime something's not an f, the whole antecedent is satisfied. You could have done, so this is not identical. What we could have done is, fx and gx, then not hx. Right? Because we're saying If something is a kettle and it's boiling quickly, then it was not watched. Yeah? Whereas we don't want this whole conditional to be satisfied by anything that's not a kettle. We want to include the requirement that it also be boiling quickly. So that's good, and that's good. We've got maybe one more in us. Oh, yeah. These Logic 2010 examples are just aging so quickly, so quickly. This was supposed to be an utterly uncontroversial statement when it was written. Okay. Democrats and Republicans who put loyalty above legality are detrimental to democracy. Okay. So, we're saying something universal here. It's a categorical claim. It's going to be for all x. Yeah? So for all x, and we've got a complex topic here, right? The topic of discussion is got some parts to it. The thing that they're saying is fairly simple. Are detrimental to democracy. So that's going to be our consequent, right? Jx. But now it's a matter of figuring out what the antecedent says. So Democrats and Republicans who put loyalty above legality. Okay. Yeah. Sorry, I haven't heard much from you. Yeah. Disjunction of two conjunctions. Walk me through it.
So the first conjunction would be is a Democrat that puts loyalty above legality.
Right? If you're a Democrat and you put loyalty above legality, or you're a Republican who puts, right? Good. That is a perfectly legitimate way of doing this antecedent. That's good. That's good. Here's another way that you could do it, which is just as good. You could say, if you're a Democrat or a Republican, and you put loyalty over legality, then you're a threat to democracy. Yeah? Either of those are just as good. Yeah?
Why do you use a disjunction for the first one?
So what we want in this case, first, this line?
Yeah.
So this is supposed to be true of both Republicans and Democrats. So we say, if you're a Democrat and you do this thing, or you're Republican and you do this thing, because we want the whole thing to be, if you put any name in here, you want to be able to say that the whole thing is true, right? So we say, look, here's Jim, and he actually is a Democrat, and he does this thing. Well, then this thing follows. But he's not this thing, but that's okay. This thing still follows, right? Or here's Bob. He's a Republican, and he does this thing, so J follows. He's not this thing, so J follows. In this case, we're doing the exact same thing here. We're just saying, look, if you're either one of these and you've got this property, then you're a threat to democracy. Okay. Okay. We've successfully brought at least some of you to a state of hopelessness and despair. So I think that's it for today. Thanks, everyone.